I did an example of Green's theorem, and I'm going to do it again, but this time numerically. So let me just give a quick recap. The link to that video going over the full details will be down below, right down there. But let me get to it. So Green's theorem is a relationship, and this is the two-dimensional Green's theorem. It's a relationship between a path integral over a closed path and a surface integral. And so it says that if I have some function, some vector function f, I use f because I like forces because I think of it as work, and I calculate the work along that path, or f dot delta r over that closed path, that would be equal to the surface area integral of this partial of f, the y component with respect to x, minus partial of f component with respect to y dA. And so I did that. So first of all, here's the vector field that I used. I used f equals x y cubed x hat plus x squared minus y squared y hat. And I want that because I want a non-conservative force. If I do the loop around the whole thing as 0, it's just not that much fun. Okay. Here is, I printed out the vector field and the path. So this is a plot of the vector field xy cubed x hat plus x squared minus y squared y hat. There you go. And so what the path I'm going to do is start here at the origin. I'm going to go along this path to the point 1, 0, and then I'm going to go up to the point 1, 2, and then back down along that line right there. And like I said, I did this. Here's the part of it. I did the work along that path. And I get negative 4/15. And if I do a surface integral of that function on the other page, I get negative 4/15. And so they worked out the same two things. But I want to do it numerically, not because it's easier, but because I think it really helps us see what's going on. I like doing things numerically because, one, it's fun, and two, it really helps us visualize what's going on. So let me just start with an explanation of a numerical integration of the path integral. And then I'll do it, and then I'll come back and I'll do a numerical integration of the surface integral. Okay, so here is, let me get a piece of paper right here. I'm going to start off with the path and the function f. So I'm going to start here. I'm going to call this point A, point B, point C. So I'm going to first go from A to B, and here's what I'm going to do. I'm going to have the vector L. And so A and B are actual vectors. Okay, so I could actually say A is the vector 0, 0, 0. B is the vector 1, 0, 0. So L would just be B minus A. L equals B minus A. And yeah, you could do that without saying this, but I like to do it this way. And then I'm going to say n is, let's say, 10. So I'm going to break this into 10 steps. So for each step, I can calculate dl, or delta L. Let's call it delta L is going to be L divided by n. And so over that path, let's say I'm going from here to there. That's my delta L. Then what I can do is to calculate the vector force. In this case, at point A, the vector force is 0. So that's not very interesting. But let's just say there is some force F. I'll draw it like that. Then I can I can assume over the length of that path over delta L that F is constant. So I can say dW equals F, the vector F dot delta L. I can just do the dot product, and that will give me the work, which is, I'm calling this path integral the work, even though it could be any vector. The work along that path would just be this constant dot product. And then I can move my ball to right there and do it again for the next delta L, where I have to recalculate the force. And then I'll do it again, recalculate the force. So over each of these little delta L's, the force at the beginning is assumed to be the force over the whole thing, which is not true. But as n gets bigger, then the step sizes get smaller and becomes more and more true. And then I can just add up dW for all those paths. It's not too hard. And then I just need to do it the same thing. I'll redefine L from here to there and do it again. And then I'll redefine L from there to there and do it again. Okay, so let's do it in Python. I'm going to do it, like I said, and then I'm going to come back and show you how to do the surface integral, because it's a little bit different. I'll do it in the same program. And I will give you the code because I'm a code giver. That means I give you the code. Okay. So I'm using Trinket VPython, web VPython in Trinket. And this is just a way to do it online. You could do this in a lot of different ways. I like this site. I also like GlowScript or webvpython.org. They're essentially the same. Okay, so let's just get started. Number one, I'm going to make point A, B, and C. And they're going to be spheres so we can see them in 3D. I'm just going to say A equals sphere. I could just make them. Now let's do it. Position equals vector 0, 0, 0. If you want to know about spheres and all that stuff, I have a whole bunch of tutorials. And if you just ask me, I'll link to the most appropriate one if you have a question. Because I'm here to share what I love, and I love this kind of stuff. Okay, so the sphere that's the location. I need the radius. So my triangle is going to be 1 by 2. So if I do a radius of, let's try 0.1. Let's just see what that looks like. And let's put B equals sphere, position equals vector 1, 0, 0. Radius equals 0.1. And C equals sphere. Position equals vector 1, 2, 0. Radius equals 0.1. I'm just going to leave them without color, so they'll be the default color. And that seems good enough. You know, if I wanted to do this, I could move it. It puts that one at the origin, kind of squishes everything down, but I think it's okay. But I'd like to make these a little bit smaller. So let's say 0, 4. 0, 4. 0, 4. I'm just guessing. Okay, that seems good. Okay, now I'm going to actually have a ball, and that ball is going to move from A to B. So it's going to start at position A, but it's going to be an actual ball. So let's say, and this is the thing I'm going to move, and I don't need the ball. It's just going to help me visualize the path integral, and I definitely want to visualize it. So let's say ball equals sphere, position equals A.pos. Radius is going to be a little bit bigger, 0.06. Color is yellow. And make trail equals true. So make trail equals true means that when it moves, it will leave a trail behind it. Okay, let's just run that. I guess I should save it too. Let's call this Green's Theorem example 1. In case I do another one, then I'll have 2. Okay, so that's my ball. Now I need to do a couple things. I can start doing it, but let's just say work equals 0. In order to find the work for each piece and add it to the total, I need to start with the total, and the total is 0. Okay, I need the vector L. L is going to be the vector B.pos minus A.pos. In, let's just put that at 50. I just picked something. Okay, so then I'll have DL is going to be L divided by N. Now I want to move the ball to B. So I'm going to say this. While ball.pos.x is less than b.pos.x. I can't say while ball.pos is less than b.pos because those are vectors. I need to pick a particular value. And since it's moving in the x direction, I'm going to use the x value. If I said the y value, it already has the same y value, so it doesn't really make sense. Now I actually want to see it move. So I'm going to say this, rate 100. This is going to say don't do more than 100 calculations per second. Actually, let's just, yeah, that's fine. I should say, let's just do it at 50. That way it'll take a second to move across. And now all I'm going to do is move the ball. That's the only thing I'm going to do right now. So I'm going to say ball.pos equals ball.pos plus DL. So the position of the ball is going to change by the value DL until it gets to position B. Okay, let's run that. Yay! Okay, that wasn't that exciting, but it did it. So now, I just want to make sure it's moving correctly. Let's do this. Let's define a function, def f, of, I'm trying to think, a vector r. Yeah. So that's my force function. I'm going to give it a whole vector, even though it only depends on x and y. So now I can just return the following, the vector. Now I'm looking at my equation. What was it? the force was x y cubed in the x hat. So that is going to be r dot x, that's the x value of my thing, times r dot y cubed. That's my x component. My y component is going to be r dot x squared minus r dot y squared. And then my z component, did I put that in parentheses? Why did I do that? Okay. My z component is going to be 0. So let's just test this. Let's print, see if it works, f of vector 1, 1, 0, 0. This will print the vector value of the force at that location. I just see if it works. Okay, so this object promise, I think it's a problem with VPython 3.1 if I change it to 3.0. Okay, so let's just check. If x is 1, I get 1 times y of 0, that's 0. And then the x squared is going to be 1 minus 0. So that seems right. It seems like it's working. Okay. So now I can calculate the d work, right? I can say the work along each step is going to be equal to the dot product, just like I said, of f at the value of r. I need to give it a vector value. So that vector value is going to be ball.pos. Ball.pos does have the x and y coordinates in it. And dl. Oh no, dl. And that's dw. Then I'm going to add that to the total work. Work equals work plus dw. And then that should do it. And let's just go, this is just for that first path. And let's print w. And now I remembered that I did this before and the work was 0 along that first path because the vector was always perpendicular to the displacement. Why did I just do that? Print. I just get excited sometimes. I just do it like that. Okay, so that doesn't mean it's correct, but it doesn't mean it's not wrong. I want to do something else. I want to actually display a value of the force as it moves along. So let's do this. Let's say F arrow equals arrow, position equals ball.pos. And then the axis is going to be equal to, let's start off with F of ball.pos. And the color is cyan. And I'm probably going to have to fix this, but let's just run it anyway. So now I need to recalculate that each time I move the ball. So I already have it all right here. After I move the ball, I'm going to actually move the arrows. So I'm going to say f arrow.pos equals ball.pos. The ball moved, and I need to redo the axis. F arrow.axis equals f of ball.pos. Okay. So that's exactly what I said. I said the force increases in the y direction, but that's why it's 0. Let's just, I think it's going to get too big once I move up, so I want to scale that. Remember, that's a vector with a length equal to a force. So there should be some scaling factor in there. Let's just say f scale equals 0.3. I don't know why I picked that. And then so the axis is going to be f scale times that. And then I need to do that down here too. F scale times. So it's just going to make the arrow a little bit smaller. I think that's okay. Okay. So there, I did the work along that first path. I need to redo it. I need to go from B to C. So we can actually just copy all this. Right there. I'm going to copy that. I'm not going to copy the work equals 0. I don't want work to be 0. And I'm going to paste it right down here. Okay, so now I need to change L. Now it's going to be from B to C. So it's going to be C.pos minus B.pos. This is still 50 steps. I'm going to leave it at 50. That's all the same. Oh, I don't need this. I don't need to redefine that. F scale, I don't need to change that. Let's just keep that. This F arrow, I don't want to change. I don't need that. Okay. And let's make it a little nicer. Okay, so DL, I do need to recalculate because I have a new L. Now, I don't want to, my loop, the ball.pos.x is at b.pos.x. So I actually want to change that to while ball.pos.y is less than c.pos.y. So I'm moving up to c.y. Rate's fine. DW, that's fine. Everything here looks okay. Let's just run it. Okay, see, I told you that force is going to get big. I knew that. Okay, it's still probably too big, but let's just leave it. But I get a non-zero work. Now let's just do the last path, going from C back to A. So I'm going to copy all this and paste it, and then I'm going to go L is A.POS minus C.POS. N is still 50. That's still the same. Now I'm going to do while ball.pos.y is greater than A is going to be greater than. I'm moving down, right? So I want to have it until it gets back down to 0. So I'm going to say A.pos.y. I think everything else should be the same. And then let's just print that out. Print W equals W. I'm not going to put units because I don't really have the right units on everything anyway. And now let's calculate it too. Let's say print WA for the analytical version. I said was -4 divided by 15. Let's just see how it agrees. Remember, we're only doing 50 steps, 50 steps, 50 steps, so we can change that. So let's run it. I mean, it's kind of exciting. Okay, that's pretty good. I get -2.078, and the answer is -2.666. Okay, so let's just go up here and change in. I guess I have to change all these. I don't have to. Let's change into 500 and the rate of 500. This one, I'm going to delete this in. They're all going to have the same in. That needs to be 500. Delete that one. No, not that one. Delete that. If I have 500 steps, I need to go faster so that it doesn't take forever. Okay, let's see what happens now. I mean, I could do 1,000 steps, but I think I've proved my point. I'm pretty happy with that. And, you know, this is a 3D thing, right? I did this in 3D. You can actually rotate this around. The path is in 3D, which is kind of cool because, you know, if I want to expand this for other applications, I could. But that's that. Okay, so now we want to do a surface area integral. Let me go back to the paper and talk about that because, like I said, I think doing this numerically helps us think about what's actually going on. We always talk about how we do these surface integrals, but doing it in Python allows us to see us do it. And the only difference is instead of having a small step size or a small piece that goes to 0, we have just small pieces. Okay, switching back to the paper. Okay, so let me get a fresh piece of paper. Okay, the first thing I want to do is this function. I need to find this function. This thing underneath here is bothering me. I need to find, remember, I'm trying to show this. I'm trying to show the surface area integral of the partial of Fy with respect to x minus the partial of Fx with respect to y dx dy is equal to -4/15. So let's get this function right here. So f is going to be equal to x y cubed x hat plus x squared minus y squared y hat. So the partial of Fy with respect to x, this is Fy. If I take the partial with that respect to y, it's going to be equal to 2x. And then the partial of Fx with respect to y is going to be equal to 3x y squared. I'm just treating the x as though it's constant, so I bring the 3 down, reduce that by 1. So now this is going to be, I'm going to call this fxy is going to be equal to 2x minus 3xy squared. That's what I want to put in this function, but I need to integrate it over this thing. So how are we going to do a double integral? Well, what we normally do, here's my surface. And so I need to know this equation. This is this top line is the equation y equals 2x, right? Because if that's 0, 0, and that's 1, 2, the equation of this line would be 2x, right? So imagine that I break this into a vertical piece. And I want to break this into squares and add up all these squares this way. So I want to integrate in the y direction. So I'm going to integrate from y equals 0 to this value, which is y equals 2x. So I'm going to go from 0 to 2x. And for each of these squares, I'm going to say dA, it's not technically an area, is going to be this function right here, fxy, that's a y, times dx dy. And in my example, dx and dy are actual physical sizes. I'm going to have a box of physical size. So let's just pick dx equals 0.1, dy equals 0.1. So this is going to be a 0.1 by 0.1 box. Now, I'm going to calculate fxy at the corner right here. Okay. So what I'm going to do is start with an x and y value. I'll calculate my function, and I'll multiply it by the size of that box. And then I will move up a distance dy. So I'm going to go dy up and do it again, dy up, do it again, dy up, and keep adding it together. And then once I'm done with that, I'm going to move over a distance dx to this spot, and then I'll start doing it over here. Okay, so I'm going to add up these rows just like that. And the nice thing here is that we can actually build this, and we can see it being built. And so it's going to be kind of fun. Does that make sense? Okay, so let's get to it. What I'm going to do is I'm going to pick an x value. Let's pick x equals 0.5. So it's halfway in between here. And I want to add up in the y direction. I don't want to do it at x equals 0 because there's only one box. There's nowhere to go. So I want to just draw these boxes going up just so we can see that how it's working. And then we'll put that inside of another loop that goes through and does it the whole way. But the first thing I'm going to do is just make this function as a function. I'm just trying to think. Should I give it a position? Yeah, let's give it a position r just like before and return a scalar value. Okay, so let's go back to Python. That's what we're really going to do. And I think it's going to be fun. I'm looking forward to it. Okay, Python is here. Okay, so we're down here. We're going to leave all this line integral stuff there. The first thing I'm going to do is do def fxy. And I can't call it f. I've already called it f. It's going to take a vector r, and then it's going to return the expression. I'm looking at my thing. It's going to be 2 times x, which is r dot x, minus 3 times r dot x times r dot y squared. Yep. Okay. So let's just test that. And I'm going to turn all these rate statements off because I don't want to have to wait 3 whole seconds for that thing to run. That's just not acceptable. Okay. And then let's go back down here and print fxy of, let's say, the vector 1, 1, 1, 1, 1, 0. Let's just see if that works. It's nice to test things before you get to it. Okay, so I get -1. Okay, so I think that's working. Okay, so I don't need that anymore. Now I'm going to say delete. Now instead of the work, I'm going to call this an area. Again, it's not an area because we're multiplying by that function. So I'm going to say a equals 0 because each square I'm going to calculate that stuff and add it to this. So I need to have a value that's 0. I need dx equals 0.1, dy equals 0.1. Now let's just say, I'm not going to draw a ball. I'm just going to I could draw a ball. Should I do a ball? Nah, let's just do a vector. Okay, so let's say RT equals, I already said where I want it, vector 0.5, what did I say? Oh yeah, x is 0.5, y is 0, z is 0. That's where I'm going to start. And I'm going to change that later. So what I'm going to do is to say, while rt.y is less than 2 times rt.x. I could just pick x and y values, but I think I want to do it this way. Then it's easier to expand into 3 dimensions. So as long as my I already have an rt.x is 0.5. So I'm going to move up to 1. So while it's that, I'm going to do the following. Number 1, I'm going to do a rate. Let's do a rate of let's say 50 again, because I want to be able to see it. And what I'm going to do is I'm going to make a box. I'm going to put a box at that location. And this box is going to have a dimension dx by dy, and then it has to have some z thickness too, otherwise it'll be super thin and you can see right through it. So I'm going to say box. I'm not going to give it a name. I'm just going to draw it. Box. The position is going to be rt. It's going to be at that location. That's the center of it. So all my boxes are going to be shifted off a little bit, but as my box size gets smaller, it's not going to matter too much. And then I'm going to say the size is going to be vector dx dy, and then the z component, let's just say it's dx divided by 4. So it'll be a lot thinner in the z direction. So I'm going to draw that box. Now I'm going to calculate the area of that box. dA is going to be equal to fxy of rt times dx times dy. And I'm going to add that to the total. A equals A plus dA. And now I need to move up. I need to move my rt location up by a factor dy. So I'm going to say rt equals rt plus vector 0 dy 0. So that's the way it's going to move. And I think that should be it. Yeah, rt, yeah. Okay, let's run it. I should save it. And let's run it. Okay, so that worked. It didn't draw the lines because when I took out the rate statement, it went so fast that you couldn't even see it. I guess we should draw it. Let's just draw this at as fast as like 5,000, like crazy fast. I do want the line. That may be too fast, but let's just see. I mean, if this video takes too long, I'm okay with that. I'm having fun. Okay. Oh, that last one went really fast, though, but that's fine. You can see the numbers building up, and I calculate that. So that seems like it's working. It does stop, but it does go over a little bit, again, because if we zoom in right here, this starts right here at y equals 0, but that's the center of the box, so it actually extends below there. You could fix this in a lot of different ways, but I don't care, because it's not going to matter as my size goes really small. Okay, so now I just need to do this starting at x equals 0 and repeating that until x gets to 1. So this whole thing, I'm going to say, I'm going to put this at 0. And then I'm going to say, while rt.x is less than 1, right? Because that's my further boundary, is 1. And this whole thing, I want to indent. So I can just tab indent that whole thing. And the rate statement, I'm actually going to, it'll be fine here. Let's make this a little bit faster. No, it was pretty fast, 50, okay. So at the beginning of each step though, I need to go over here and to say rt.y equals 0. Because I just increase y up all the way to the top. When I move to the next step over, I need to go back down to y equals 0. That looks good. Now, at the end of that loop, I do need to do this. I need to move over one position. So I'm going to say rt equals rt plus vector dx 0, 0, which is the same as dy, and that's fine. And I think that should work. And let's just go ahead and say print a equals a. And it should be the same as WA negative 2.66. I'm not going to reprint that. Okay, let's just see what happens here. See, I love that. Okay, it's too big, but that's fine. But I love that. You can see how it's adding up in the y direction and moving over, and it's slow, and you can see all the pieces. Now, we can do some work here to make this cooler, and I'm going to, just because I can. But the first thing I should do is to make the step size smaller. I was thinking about making the thickness related to the function fxy, the z thickness. I wonder if you could see that. I think you could. Let's just try it. And let's just see what it looks like. Okay, so down here when I make the box, I'm not going to say the z component is I need a scale. Let's call this z scale equals 0.01. I don't really know how big that's going to be. And then for the box, I'm going to say z scale times magnitude, oh, it is already, times f xy of rt. So the thickness of each box I draw depends on the value of fxy. And just for fun, let's just see what happens. I think you should be able to see it then. Yeah, it shows up a little bit. You can see these are a little bit bigger. So let's make that scale 6. I'm just trying to play around with the size of it. Yeah, there you go. Okay, so now, of course, that's not perfect, but it's cool. And another thing I could do, I could change that. Look at that. That's cool. Come on. One thing I would probably do is just have them go just in the z direction. So the y component of the ball, I'd have to shift. No, the z component I'd have to shift. Should I do that? I think not. And another thing you could do is make the box size a little bit smaller than dx, so that there'd be boundaries between them. You could change the color or the opacity. Those will all be fun things to do, but I'm going to leave it like that. So the next thing I'm going to do is I'm just going to make dx smaller. Let's say 0 and 0. Now to do that, I should make this move faster, and let's see what happens there. Okay, so now you can see it's building slower. Of course, it's doing a lot more calculations. That just builds up the anticipation. But you notice it's filling in really nice. You don't see this bleeding over as much. And you can see the three-dimensionality of it. Yeah. That's pretty cool. I should have done it even faster, but I kind of like it better with the smaller blocks. It just looks a little bit better. Yeah, because you can see those blocks. But here you can see that A is closer to that. It's not exactly. So let's just make this a little bit smaller. I want it to be even closer. 0.05. I know I'm going. You're thinking, no, it's too much. She can't handle it. She can't take it anymore. Okay, that's fine. But we're going to do it anyway. So 5,000. Let's do it as fast as we can to see what happens. Okay, it seems like it's filling up pretty fast now. That's pretty good. Oh, now it's getting slower. You know, you got to realize how many objects this program is drawing. It's drawing a whole bunch of objects. You know, you can't even really see them. But that is pretty cool. Okay, so that's that. So I get down here, the area, I get about -4/15, and that's that. So that's that surface integral. And I really like this surface integral, again, because you can see how it is. If you want, what you can do as a homework is to go back and take this integration. In this case, I integrated by adding up in the y direction, then moving over in the x direction. You could actually do it the other way. You could add up in the x direction, then move up the y direction. You should get the same thing. See if you can modify the code to do that. You could also take, for the line integral, you could add a little DL vector, so you could draw two vectors and see how they combine. It's all fun. So that is that. Green's theorem, 2 dimensions, numerically, with some visualizations. I like it.